Hi, welcome to All Things One Place, video number 2. And we're going to do a little bit of waveform analysis on various light bulbs and look at how the power is consumed. Basically, we're just going to look at the current waveforms and the voltage waveforms. The voltage waveform is going to stay the same throughout the videos because it's mains AC, and then our current waveforms are going to be kind of all over the place. Just going to go over a little bit of the test setup here. So first thing we do is we have an isolation transformer, which is this guy over here. That's going around plugging into this red box over here, which is a variac supply, so we can just adjust the voltage, get it close as we can to 120 volts just for somewhat even comparison. And then sensing the voltage. So we're going into this next. This is just a little, really cheapo power analyzer, nothing fancy, but functional enough. So this is then feeding out to some overkill size power cords here and going into this box, which is just the connection box. It just gives us a lot of ports to be able to tap off voltages or current and things like that. So what we're doing there is we are tapping the voltage off, going into a differential high voltage probe, which is then going into an oscilloscope. And then we also have coming out of this box, going back out to the socket, is a current transformer essentially on the output side, and we have 4 windings going around here just to get better signal to noise ratio, because this is a 65 amp sensor, so it's not going to be very sensitive to like these LED bulbs where we're only measuring point something amps. So we're using the 4 windings just to get a little bit better of a signal out of that. Just as a note, you have to divide by 4 of the values that are going to be on the scope screen. So here's the various bulbs that are going to be tested. We got an Osram, just a basic LED light bulb. It's a pretty modern one. We have an IKEA desk lamp, nothing special. I'm not going to go through the whole list. We'll just get into it right now. So here's the Osram bulb. It's not anything special, just a regular light bulb. The waveform's a little bit square-like. It's got a pretty good power factor though, so it's one of the better demonstrations. And then it's in phase, so that's good. So here we'll actually get into it. So you can see the waveform pretty much kind of squares off. It's almost like a triangle shape, but it's definitely not a sine wave, that's for sure. You can see this thing kind of bouncing around like that. Not fantastic. This blue one is the voltage waveform, and this yellow one is the current waveform. Alright, let's take a look at this IKEA desk lamp. Power factor's going a little lower now. Again, none of these are including THD. I don't have any fancy equipment that's good enough to include that information, so just old school power factor, just basically the phase angle. Low watt, but the waveform was pretty spiky. So here we take a look at that, you'll see it's got some pretty terribleness going on here. I'm not sure why there's a big spike and then another big spike, so this is definitely some weirdness. I don't even know what kind of supply this is that would cause this big spike here and then a secondary big spike here. Not a capacitive dropper, it's definitely some kind of switching supply, but very strange waveform. The next one, we got that Utilitech. This is the one I repaired in the last video. The dome has gone missing directly to the trash can, which is probably where this bulb's going to ultimately be headed. It's got plans. I got some plans for this thing. We're gonna destroy it a lot more, so that'll be another video. But yeah, we take a look at the meter over here. We can see the current is actually higher, and the watts are a little bit higher, but not really much. So that bad power factor is telling you that the waveform is going to be bad. And here it is. You can see it basically doesn't draw any current for a significant portion of the time, and then it just draws these giant spikes. And this is very much what a capacitor attached to a bridge rectifier looks like. So although this is a capacitive dropper, it almost appears like that part of the circuit isn't really doing anything. We're going to mess around with this and we'll see if we can make this look a little better. The next one is just a GE
basic light bulb, pretty good power factor, near sine like waveform, a little bit out of phase. You know, it's not amazing, but it's really not bad, and definitely looks just like a normal light bulb. I don't know if you pick it up, it feels like a normal light bulb. But waveform, you can see, is a little bit, kind of a little bit funny. Definitely doesn't follow the sine wave shape of the voltage, so that's where we're losing our power factors. It's just not quite in line, and it's just a little bit weird. All right, the next one, we got an incandescent bulb. Does anybody still use these? Leave a comment down below if you do. 1.00 power factor, basically perfect. Perfect phase. The current and the voltage look exactly the same. But the one thing is to keep note of here is that the current overall is higher than any of the other bulbs. So no matter what, even with a terrible power factor, this thing's still using a lot of power. But here's the trick. Look at these things. They look great. Just this nice perfect sine wave for both the current and the voltage, which is about as ideal as you can get. Next one, we got a compact fluorescent. I don't know if anybody's still using these. Most of them, I think, be burned out by now, but I found one in a bin somewhere, so hooked it up, checked it out. You can see the current on this one's pretty terrible. Power factor's pretty bad. And this actually wasn't warmed up yet, so these numbers are even a little bit higher than this. And yeah, so this thing's using, you can see it's 11 watts, but it's using 0.15 amps. So this thing's, if you saw that other bulb, the incandescent, it was 0.3 amps and 40 watts. So this is effectively using 20 watts of energy, which is not so great when you're talking about current. It's actually rated appropriately though, so it gives you the information that you need. And this is the current waveform for this thing, and this thing is probably one of the worst out of all of them. It's very, very large spikes here. Kind of similar to that capacitive dropper, although this is not a capacitive dropper. It is a switching power supply. But I wonder what the beginning of that circuit must look just like a capacitive dropper, or in the case of that Utilitech bulb, it's more like a bridge rectifier and a big capacitor. Because like I say, that Utilitech bulb kind of follows the same form as this. And then last but not least, we have an old Sylvania bulb. It's 12 watt rated. Drew a little bit more than that, but great power factor. It's pretty close to a sine wave, and it was in phase. I mean, the power factor is fantastic on this thing. I'm not sure how they got it so good. I guess they put a lot of money into it. This was also a really expensive bulb when it came out. A lot of these newer bulbs are like $2 or $3. This one was 20. And here's the wave shape. Yeah, it's great. It's about as ideal as you can get, because remember, this is a switching power supply, so getting a shape like that is awesome. I'm not getting into any whether these are dimmable or not dimmable bulbs. I'm pretty sure this Sylvania one is a dimmable bulb.
Okay, we're going to just demonstrate some of these bulbs here. So we're going to first try out this Osram bulb. There it is. It doesn't do too bad. Looks like a pretty normal light bulb. Alright, next we're going to plug in this IKEA desk lamp. See, that one just kind of makes a little spot. Plug our socket back in here. And we're going to try out the danger bulb here, the one I repaired in video 1. There it is. Let's try out this GE LED bulb. That one just looks like a normal light bulb, doesn't it? Nice even light throughout it. Next we got the GE Incandescent bulb. Looks very, very similar to that last LED bulb. Perfect power factor though. You get that 1.000. Of course, leave that on too long, this will get real hot. GE twisty bulb here, compact fluorescent. This one actually takes a little while to warm up. It's actually kind of dim at first, and you leave it for a little while and it'll just start getting brighter and brighter, and eventually it'll get up to the 13 watts of power it's rated for. It does take a little while to get there though, and I'm not going to do that. And last, I got a really old Sylvania bulb, which in terms of the LED shootout here, maybe one of the better bulbs in terms of the, you know, condition of the power that it draws, but it is certainly not the most efficient, and it definitely throws the light in one direction.
Let's go over a couple of something fell. Go over a couple summaries here. We have you know, LED bulbs create a wide variety of wave shapes. Obviously we saw some really spiky ones, some fall almost like a sine wave, and it's going to change how basically how they perform. Some bulbs use a significant amount of current even if the power is low. Now this is power factor. This is like a whole other topic. I'm not really going to get too much into that. Certainly a topic for the future. And then even with an old style CFL bulb, the incandescent is still twice as much current, even if the waveform is a lot more pretty. You know, in terms of the grid being happy, incandescent bulbs are really easy to power because as the voltage increases, the current increases. That CFL bulb, it didn't do that at all. It just this giant spikes, so all the current is drawn really fast and all of a sudden, as opposed to in a nice smooth waveform. It's not very nice to have that. Dimmers don't work on some of these, you know. Try and dim that CFL and see what happens. It's just going to shut off or flicker, or it's just not going to work. So looking at the wave shape, and then phase angle controllers, or that's what most dimmers are. You know, triac dimmer or something like that. They're just, you know, certain bulb types just aren't going to behave well when you're cutting off a piece of the waveform. It's not drawing any current over that section of the waveform anyway, so the dimmer can't even fire correctly. And then yeah, there's basically too many things to cover, so it's kind of a huge topic. I'm just kind of trying to go over it quick. But yeah, this is just a little video to kind of talk about some of the different kinds of light bulbs and take a look at what some of the wave shapes look like, and that's about it. Thanks for watching. Like and subscribe.